Hello, my name is Rajesh Kumar. This is my second annual progress seminar. My topic is photonic bound state in the continuum and its application. So, bound state in the continuum. So, bound state and continuum are two opposite words. So, bound state means one discrete value, discrete state, while in continuum where all the states are available. So, photon is bounded even when all the surrounding states are available to couple, but it did not couple and it remains in a single bound state. So this is the meaning. So one simple funny analogy is that this horse is bounded by this chair. So by its bounded mentality, it is thinking it is bounded, but uh, it can move anywhere. So the states are available for this horse. So this is the example of this photon bound state in continuum. So these are my recent publications. uh, the talk outline is such that I will go through the introduction to bound state in quantum, abbreviated as BIC, and then BIC in silicon nitride metasurfaces and its strong coupling with TMDC materials. Then I will go this BIC in low cost polymer metasurfaces as well as in bulk TMDCs. So as previously in my last APS I told that this bound state in continuum can be explained on the multipolar decomposition, that is multipolar origin of this BIC. So if we choose any arbitrary shape of metasurfaces has one unit cell, then the far field of the due to this unit cell is the sum of all these multipolar, like dipole moment, toroidal dipole, and magnetic dipole, quadrupole, and octopole as well. So the BIC is of two types. One is symmetry protected VIC, another is accidental VIC. So the symmetry protected VIC is when all the dipoles are presented do not radiate it in normal direction, then this is known as symmetry protected VIC, while the accidental VIC happens when the multipoles are combined such that they cancel out each other's radiation in particular direction. So this is called accidental VIC. So as well in the last APS I present the reproduced result of this cavity, which is taken from this paper. So they take TiO2 material and formed a asymmetric disk. So the reflectance is matched such that the line width of this reflectance spectrum is equal to the line width of this WS2, and the peak position is also the same as WS2 PL peak, we can say. So then they put it together and found this strong coupling between these cavity and WS2. So I reproduced in the last one. Next then I did this BIC in our silicon nitride metasurface. So we choose silicon nitride, which is CMOS compatible material. So we take this bimin plus bimax. So bimin is the length downward from the center, while bimax is the length of this line uh, upward to the center. So the total width is bimin plus bimax, and when this bimin equal to bimax, the structure is considered as a symmetric structure, because this sigma 0 the area of this region, sigma 1 is area of this region, then this asymmetry parameter is defined 1 minus sigma 1 upon sigma 0. So if bimin equal to bimax, so sigma 1 will be equal to sigma 0. So this asymmetry will be 0. So at this symmetric structure, we found this BIC at 1.68, and then we introduced this asymmetry parameter and plotted this reflectance graph with the function of asymmetry parameter. So as the asymmetry increases, the radiation loss or the width of this reflective spectrum is increasing, as well shift in energy or wavelength. The peak is shifting on the axis of energy also. So if we plot this gamma as a function of asymmetry parameter, so this gamma is calculated by fitting the Fano fitting of this reflectance spectrum calculated in COMSOL, and this gamma x is the line width of any exciton. It may be WSC2. For here we plotted for WSC2 this gamma x. So if we want to study the coupling between WSC2 and this metasurface cavity, so we have to choose this asymmetry parameters and so on. Similarly, we plotted the Q factor with the function log Q factor versus log symmetry. So this slope of line is 2, which is which is consistent with the literature relation, which is for quasi VIC, this Q directly proportional to alpha to the power minus 2. So this graph indicates that this is quasi VIC mode of this cavity. Similarly, for the further confirmation, I did the multipolar decomposition of this mode, and we found that the dipole, which has the major contribution to the radiation loss, has 0, and the contribution in radiation is only due to toroidal and magnetic quadrupole, which has low radiative loss contribution in the normal direction. So, and also for two different asymmetry parameter, if we compare, the electric field confinement is larger at lower alpha, and as it goes to 0, this confinement will be large. Confinement will be large. So that is another definition of BIC, that the confinement of the light is very high, so it did not radiate outside, and this radiate line is measurement of line width, which is 0 in BIC. Similarly, if we see the contribution, so this toroidal dipole, this is orange one, is become broader as this gamma C increasing, or asymmetry parameter is increasing. So we can say that the radiation which is increasing is due to increasing the toroidal dipole radiation. uh, so this is another confirmation for the quasi BIC. So next, after confirming that our structure has quasi BIC, we test the stability of this quasi BIC mode in our structure. So for that we take radius for different radius and three different periodicity combination. So then whole 9 combination be plotted here. So if we see, the trend is similar and the slope is only deviated from 0.01 per nanometer. So it means we can we have relation Q is directly proportional to alpha to the power minus 2. So for some reason we can hold that relation in change in radius. Similarly, if we change the periodicity, still this relation is hold. So we can say this quasi BIC mode is stable in this metasurface. So what is the use of this quasi BIC? So this quasi BIC cavity we are going to use in strong coupling with monolayer TMDC monolayer. For main TMDC monolayer is WS2, WSE2, MOS2 and MOSE2. So for strong coupling condition, this omega, like this is the cavity and this is exciton, and the exchange energy between this cavity and exciton is omega. Means so this exchange energy should be greater than this material loss, then we are here in the strong coupling region. So this is the main condition. So if we say omega upon gamma m, this should be greater than 1, which will come further also. We did one analysis on basis of this relation. So the strong polyton coupling with BIC, we checked with WS2, WSE2 and MOSE2 and MOS2 for the different parameters, because the main condition for the strong coupling is the line width should be equal, as well as the peak position of this exciton and this cavity should be equal. So we optimized for all four the same geometry uh, at different parameters gives us the strong polytonic coupling with all four TMDC. So after that, before fabrication, we check the fabrication robustness in strong polyton coupling using this method. We following the another method, we can use the different parameter for the different disk in the structure array, but for that we need large area simulation, which needs the more computational resource. But this is the simple method what we did here. We have this optimized parameter, this red spot, and for the radius and bimax, then we vary this bimax from plus minus 7% from the optimized parameter, and radius we vary plus minus 15 percent from the optimized parameter for the radius. Then we got total 25 points which we simulate in the console and extract the absorption spectrum at all these 25 uh, points. Then we use the interpolation method in MATLAB, written code, self-written code. So we graded it by 1000 by 1000 point. So total 1000 by 1000 multiply 1000 points are here for different parameters. The absorption spectrum we also have by the interpolation method. Then we choose a random 500 points for this one with the different deviation sigma value. 1 nanometer, 5 nanometer, 10 and 15 are shown here. So the distribution is mm, 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 what it is, Gaussian distribution we took, and then we averaged all these 500 points absorption spectrum to calculate for single sigma 1 and so on. Similarly, then after calculating the absorption for different sigma, we plotted this with the relation this omega is great should be greater than gamma c plus gamma c plus gamma x should be greater than 1. So where gamma x and gamma c is the line width of exciton and cavity. So we did the same simulation with the cavity only, and then uh, with monolayer also. Then we plotted this omega is the Rabi splitting between these two polyton, maximum Rabi maximum splitting between these two, and then we plotted, and we say here that for the deviation of 10 nanometer we are still getting the polyton coupling, because this condition is still hold. This omega upon gamma x plus gamma c should be greater than 1. So this why we choose this deviation, like when we fabricate the structure, so all the disk will not come for the same parameter. Some will come at uh, from deviation from which we give, that is optimized parameter. So we took radius and slotted disk which will be mainly varied in EVL process. So this is the aim of this work, and this is concluded. And on archive also, and we are communicating in the journal. So for the next, we tried this BIC in bulk TMDC metasurfaces. So for that, we choose WSC2, which have a background permeability 25 nanometer 25, so have a higher refractive index than silicon also. So we are getting here, if you see, this mode has the symmetry protected VIC. This mode also have symmetry protected VIC. This mode have also this yellow, all three yellow mode are symmetry protected VIC, while this yellow points we can consider as accidental VIC. So first we optimize the parameter in legume, which has normalized frequency or at this axis, which is AYL. So we can calculate according to our need of spectrum peak. Let's if we want at 750, then periodicity A can be calculated as 0.44 multiplied by this L. So we gave these parameters to the console, and we got the similar electric field profile for the eigen frequency mode at 766 nanometer. So this is of our interest, mode of our interest, and also have the highest Q factor in between all the modes. So we can consider this as a BIC mode. And further we are on fabrication of this structure to realize the experimentally. So and one another parallel work is going on, this BIC in polymer metasurface. So if we calculate this legume, this on in legume, so we are getting this one accidental BIC in this polymer. Why we choose polymer metasurfaces? Because they are one is low refractive index material, as well as low cost material also. So we are searching in this one. So after optimizing this parameter, we also optimize the fabrication for this thing, and we are getting good images, this same images, and these are at the parameters of this one. So my further aim is to check this experimentally, this mode is coming or not. So and parallelly we also growing this monolayers of WS2. So here is this optical images of this monolayer, and this is large area monolayer, and this triangle we take the Raman spectrum. So for the WS2, these three modes are dominant, E1G, which is in plane mode, and A1G, out of plane mode, and this 2LA is the acoustic phononic mode. So at the room temperature, second order acoustic phonon mode is dominant than in plane vibration mode. So and the in literature it is the difference between these two modes is 66 centimeter inverse. So we are getting in the good match with the literature, so we consider as a monolayer, and we are also getting this PL. So we optimized this with collaboration of Anuj, and the summary is we explored the BIC in split disc silicon nitride metasurface, and then we study the strong polytonic coupling with TMDC monolayer, and we also study the fabrication robustness of strongly coupled polyton, and we fabricated metasurface with EVL lithography, and also grow the TMDC for experimentally demonstration of strong polyton coupling. And we also explored the BIC in low cost polymer material, and optimized the fabrication for the same as so. And my this year future work plan will be to making an optical setup for characterization of characterization of BIC mode, and experimental verification of the work presented here, which is theoretical only, and the experimental demonstration of BIC in low cost polymer material as well. End goal is to use the exotic BIC phenomena to make low cost high sensitive sensor to improve healthcare facility. And I would like to thank to my supervisor as well as my lab members and the funding agency as well. Thank you.